Okay, so this is our first lecture in rational expressions. So we're going to start with reducing and finding domain, and then we're going to do multiplication and division. And if there's a little bit of time left over, we might even start addition and or subtraction in this video. Otherwise, we'll do that in the next video. So let's get started. A rational expression is just a fraction. So our rational expression is some expression divided by another expression, okay? So a couple of things to keep in mind. The first thing is that if you have an expression times another expression, and in the denominator, you have the same expression repeated twice, so one in the numerator and one in the denominator, and we're multiplying. Here we can cancel, okay? We can take out this k, and we could say that this is p over q. Essentially, all that we did here is we multiplied by 1. K over k is equal to 1, and anything times 1 is itself. This we already know. About this even when we were doing other proofs, that when we were sorry, I'm trying to think which proof we used it in. We used it in the proof that anything raised to the 0 power is equal to 1, and we said anything times 1 is itself is the multiplicative property of the identity property of multiplication. Okay, so anything times 1 is itself. We can cancel this out because it is multiplication and division are here interchangeable in this order of operations here. So we can cancel. We can do the division before we do the multiplication. That's okay here. Okay. Another thing to note is that suppose that we have an expression of one rational expression divided by another rational expression, where the denominator of both of these expressions is the same. I want you to remember what we've said it in the past. We said it that in order to get rid of this denominator, because we do not like fractions and fractions, just like we don't like radicals in the denominator, we don't like complex numbers in the denominator, we do not like fractions in a denominator. So to get rid of it, we can multiply by its reciprocal. That means that this whole thing will cancel, but what we do on top, we have to do on what we do on bottom, we have to do on top. But when we do this on top, this becomes pk over qk, and we already know that this is p over q. Okay, so two things just to help you remember. Okay, so let's just take some basic fractions, just with just numbers, nothing, not an expression, but just numbers. Let's say that we have 3 over 2 times 4 over 2. This is just to refresh your memory. Okay, we multiply all the way across on both the top and the bottom. So we get 3 times 4 over 2 times 2. Obviously, you would not need to write out all of these steps. I'm doing it here just so that you could see what's going on. So we multiply the top, we multiply the bottom, and we get 12 over 4. You've seen this before. You saw it when we were doing exponential expressions and we were simplifying these complicated expressions. And we said if you have one exponential expression times another exponential expression, you can essentially just extend this line here. And that's what we're doing. We're just extending our line and multiplying the tops and the bottoms. Okay. By the same token, if we have something like 7 over 6 times 5 over 6 we can multiply straight across. So we have 7 times 5 over 6 times 6, which gives us 35 over 36. Now, if we go back up here for a second, we get 12 over 4. But one thing that you always want to remember is with any fraction, including fractions with rational expressions in them, you always want to reduce. So 12 over 4 is equal to 3. So don't forget to reduce your fractions. Okay, a couple of other notes before we get started. We know from domain, when we were trying to figure out the domain of functions, we were looking particularly at rational expressions. And if we have an expression x squared minus 9 over x minus 3, okay, if we're trying to find the domain, we know that x minus 3 can't be 0, because if it were, it would make this undefined. So here, x minus 3 can't be 0, or this expression would be undefined. So the domain, if we put this in standard notation or set notation, we would say x such that x is not equal to 3. So don't forget about your domain, okay? Another note here is that if we have something like 6 minus 3, this is equal to 3. Now, if we switch the order of this, and we said 3 minus 6 instead, now this is equal to negative 3. So when you switch the order around a multiplication sign, what's happening is our answers become negatives of each other. So for example, 6 minus 4 is 2, but 4 minus 6 is negative 2. 9 minus 3 is 6. But 3 minus 9 is negative 6, okay? So what we're saying is that if we have a minus b, if we subtract two numbers, our answer, this is the same thing as negative b minus a, right? So if this is a minus b and this is b minus a, what we're doing is we're saying a minus b is the negative of this. So a minus b is 6. That's the negative of 3 minus 9, which is negative 6. And negative of negative 6 is a positive 6. Now here's why that's important. We know that a minus b over a minus b is 1. The reason why this is helpful is that if we have a minus b over b minus a, this is equal to negative 1. Okay, so these are just some things to note as we work with these rational expressions. And the only time that this isn't true is if a equals b. So we have to say as long as a is not equal to b, because if a equals b, then this is 0, a minus b is 0, and this would be undefined, right? Because we can't have b minus a being 0. So that's why we put this in here. And a lot of times you're going to see things like this, and it's a formality, okay? In other words, we're putting it in there because we need to make sure that everybody knows that our denominator can't be 0. But these are things that you should automatically be thinking about and saying, oh yeah, denominator can't be 0 because it would be undefined, okay? Okay, so the first thing that we're going to look at is just reducing, okay? So we're not reducing just any old fraction, we're reducing a rational expression. Again, it's not that you've never done this before, it's just that we've never formally talked about it. So let's take an example, okay? say that we have y squared minus 5y minus 6 over y squared minus 1. Okay, so the first thing that we have to do here is we need to see if there's anything that we can now please be aware, we cannot cancel this y squared, okay? So the reason why we can't cancel the y squared is order of operation. So these are things that we talked about at the, I think it was the second day of class, that there is an invisible parentheses around here. Okay, we can't see it, but it's there, which means that we have to do the subtraction first before we can cancel anything out here, okay? The only time that you can cancel is if what you're canceling has a multiplication sign next to it. So that's not the case here. There's a subtraction sign here, a subtraction sign here. So the next thing that you're going to look to do is you're going to look to factor, okay? So in each of these cases, you can look to see if there's common factor first. A factor that's common to every term. Now that's not the case in either the top or the bottom. So we have to actually factor this out. These are quadratics, okay? In both cases, the a is equal to 1, so it's not that difficult to factor. So y squared minus 5y minus 6. I'll show the steps for factoring this one, but in general, in the future ones that we do here, I'm not going to show all of the different steps, just because this should be second nature to you already. And if it's not, then you should make sure that you go through and practice. Okay? So if you remember, to factor out y squared minus 5y minus 6, you need two numbers that multiply to negative 6 and add to negative 5. Okay? So this is to factor the numerator. So two numbers that multiply to negative 6 and add to negative 5 are negative 6 and positive 1. Which means that this y squared minus 5y minus 6 factors to y minus 6 times y plus 1. Now the bottom, y squared minus 1, is a difference of squares. So it's y plus 1 times y minus 1. This was something else that we talked about when we were talking about factoring polynomials, right? We were doing factoring by grouping, and we said sometimes you're left over with a difference of squares. So the difference of squares says that we're subtracting two perfect squares, and that factors to a plus b times a minus b. Okay, the middle terms will cancel. We get a plus BA and a minus BA, so that goes away. And then the A times A is A squared, and the B times negative B is a negative B squared. That's why it's a difference of squares, okay? And now from here, we can see, okay, is there anything that we can cross out? And we actually have a y plus 1 in common on both the top and the bottom, okay? And that can cancel because the y plus 1 is being multiplied by y minus 6. Here the y plus 1 is being multiplied by y minus 1. So now we have our final answer. So our final answer is just y minus 6 over y minus 1. Okay. And we've reduced the rational expression. So let's just summarize what we did here. Okay, and it's going to be the same for every type of expression that we, for every type of rational expression that we are trying to simplify. Okay, so the first thing is we want to factor the numerator and the denominator. Typically in the problems that we do, The numerator and the denominator are going to be either linear or quadratic. So you're not going to have to do factoring by cubics, or factor by grouping. The thing that I would emphasize here is that before you do anything, okay, you should look for, does every term have a common factor? Because that's going to make any other factoring that you have to do easier. And that's true of the fraction as a whole and of just the numerator and just the denominator. Because you would factor that out first. And we'll see some examples of this in some of the problems that we do. Okay. And then the second thing is to reduce. Essentially what we're doing is we're canceling, and canceling means by the numerator and the denominator. And I'm going to put a note here that says pay attention to order of operations, because I want you to remember that it needs to be multiplied. This is what I was talking about before, that you can't just cancel out the y squared. Okay, and what I was saying before, where I kind of stopped mid-sentence, is that the reason why we can cancel this out, what we're really doing is we're saying y plus 1 over y plus 1 is 1. And this is what we were talking about here, that you're multiplying by 1. So if you're multiplying by 1, we don't need these extra expressions in here to make it look more complicated. We can simplify it to just this p over q. So that's what we mean by reducing. We're taking away some of the terms that aren't necessary anymore. Okay? Okay, a couple of other things about domain here. Okay, our y cannot equal 1, but it also can't equal negative 1. Okay, so the domain here the only thing that we have to worry about is that our denominator can't equal 0. So in this case, and keep in mind that we're saying y here, but that's because y is being used as our variable. So it's not like this is equal to y. What we're doing is we're saying, okay, y can't equal 1 and y can't equal negative 1. Okay, so it's just, this is just because this is the variable that we're using. Now, I've gotten some questions in the past that says, okay, well, why can't y equal negative 1? Because this cancels. And actually, if you were to graph this, which we will talk about in, I don't think it's the next lecture, it might be the lecture after that. The reason why you can't just cross this out, the reason why you can't just say, okay, well, this gets crossed out, so y can be negative 1, is because we have to look at the original, okay? And if you were to look at this on a graph, actually, at y equals negative 1, there's going to be a hole in the graph. Y can't be negative 1 because in the original expression, we would get 0. So these equations, these expressions are equal to each other, but we want to be careful about what we mean by equal. It's not that every single point is the same. Every single point is the same except when y equals negative 1, okay? And when y equals 1, because in those cases, the graph actually doesn't exist. So on the graph, if we were to plug in a number, it might be fine, but on a graph, y equals -1 just doesn't exist because it would make this expression undefined, okay? And when we start graphing rational expressions, I think that that'll make a little bit more sense too. Okay, let's take another example. So I'm going to label this, I'll just put this down here as just a bunch of examples. And again, as we go through these, I would encourage you to sort of stop, do it yourself, and then see if you get the right answer, okay? So the next one is 2a squared minus 8. And then on the bottom, we have 4a squared minus 12a plus 8. Okay. And we can go through and we can factor this. Okay, so that would be our first step to factor. Now, there is a term that everything has in common. Every single term has a 2 in common. So we could take that out, or we could wait and factor the numerator and then factor the denominator, which is something I would probably encourage. But you absolutely can take out a 2 from every single term. If you took out a 2 from every single term, you would get an a squared minus 4 here, and you would get a 2a squared minus 6a plus 4 here. So it's kind of up to you how you do it. As I do this, I'm going to treat the denominator and the numerator kind of as separate entities. And then at the very end, I'll work with the 2 of them together. Okay, so we have an a squared, a 2a squared minus 8 here. So as we said, we can factor out a 2. So this becomes 2 times a squared minus 4. There are always going to be multiple ways potentially of doing this, so it's kind of up to you. Okay, and we could factor out a 4 in the denominator. So we're going to pull out a 4. And we get a squared minus 3a plus 2. Okay. Now this 2 over 4 we can reduce. I would wait to reduce until the very end. So I would completely factor the numerator, completely factor the denominator, and then try reducing. Okay? And the only reason for doing that is 1, so that you don't forget to factor something, and 2, so that at the very end you don't accidentally cancel something out and then forget that you have to include it in your domain. Okay, so 2 notes here. First one is, here we have a difference of squares. This is actually only 1 note. Okay, so as we factor that, that's a difference of squares. So don't forget, you're not canceling anything yet, so the 2 stays. And at a squared minus 4, the difference of squares is a plus 2 times a minus 2. And then on the bottom we have a 4. And this one we need 2 numbers that multiply to 2 and add to -3, and that's an a minus 2 and an a minus 1. Okay. Multiply to 2, so we have -2 and -1, that gives us the positive 2, and -2 and -1 gives us the -3. Okay. Okay, so now just before we go on, we're just going to make a note as to our domain, because we already know that we want to do it before we start trying to reduce anything rather than after. Okay, so our domain here, and here we're going to use a, because that's the variable that we're using. And what's going to make the denominator 0? 2, so a can't equal 2. And 1, so a can't equal 1. Okay, both of these would make the denominator 0. Notice 2 minus 2 is 0, but we can also do it like we've done it before. A minus 2 equals 0, so A equals 2, okay? This is a quadratic. We're saying when is this quadratic equal to 0, so we factor it, and we set each factor equal to 0. Okay. Now at this point, we can start reducing. The A minus 2 and A minus 2 is 1, okay? So we can take that out. And then 2 goes into 4 twice, so 2 over 4 is the same thing as 1/2. So our final answer here, I'll put the 1 up here, okay? 2 over 4 is 1/2. So our final answer here is just A plus 2. We don't need to put in the 1. And then over 2 times A minus 1. And we don't need to multiply, okay? So we don't have to write 2A minus 2 on bottom. It's just changing the way that the expression is written. It's not reducing it. It's just a different way of writing it. So you don't have to multiply. That's completely up to you. You would get no points off if you did because it's not incorrect. You're not adding things to this expression. You're just changing the way that you're writing it, okay? Okay, let's take another example. So let's say that we have x squared minus 25 over 5 minus x. So again, consider pausing the video and trying to do this on your own. So all we're doing is we are reducing our rational expression. We're simplifying this rational expression. There's nothing that we can cancel, okay, because all of these things are attached to minus signs, so there are invisible parentheses. So our first step is to factor. So x squared minus 25 can be factored. This is a difference of squares. X squared is a perfect square, 25 is a perfect square. So one thing that you should always look for is a difference of squares. We said that you should look for, to see if every term has a factor in common. You should also, when you factor, you should also look for a difference of squares. So if we go back here, we said always look to see if every term has a factor in common. I'm going to add in here. And to look for a difference of squares, because if you miss that, you could be missing something that can be factored. Okay, so let's go back to where we were before. So this is an example where we have an x minus 5 and a 5 minus x. And these are opposites of each other. So when they cancel, this is a minus b over b minus a. And we said that this becomes a negative 1. So I'll put this as a note on the side. Right? A minus b over b minus a is equal to negative 1. So that's something that you should also look for. So that means that what we're left with, there is no denominator. Do not write a denominator if there isn't one. So this is just negative x plus 5. And again, you don't have to distribute the negative. You absolutely can. You'll get full credit for something like that. It's just a different way of writing it. You're not making it more or less complex by doing that. Okay, let's take another one then. So we're going to take a to the 4th minus 81 over a minus 3. Okay, so a to the 4th minus 81. This is a difference of squares. a to the 4th is a perfect square, and so is 81. So if we factor this using the difference of squares, we get a squared plus 9 and a squared minus 9 over a minus 3. Now, typically we would say, okay, there's nothing that we can do, but once again, we actually have a difference of squares. The a squared minus 9 is also a difference of squares. A squared plus 9 we can't do anything with. So a squared plus 9 just stays. But a squared minus 9 is a plus 3 times a minus 3. Okay. Denominator can't be factored. But here, a minus 3 can be canceled. Okay, again, when we say canceled, we're saying that it's equal to 1, so the expressions are not necessary to put in there. So our final answer here is just a squared plus 9 times a minus 3. That's in its simplest form. Okay, I want to do the domain for this one. So the domain our variable is a, so we're going to put a. Remember, this line is such that. And then a can equal 3 here. Okay, and then up here we didn't do a domain for the last problem, so let's put that in there. Here we're using x. X is our variable. And how would we get a denominator of 0? If x is equal to 5. Okay, so this is the same thing. You would say, okay, when does 5 minus x equal 0? 5 minus x equals 0 when x is 5. So x can't be 5, because otherwise it would be undefined. Okay? And typically when you reduce fractions, when you're being asked to reduce fractions, you may not be asked to find the domain. Okay, but when you graph, you have to. Okay, let's take a few others. Let's say that we have, so notice here, just a note that we factored. There was nothing that we could cancel. You should make sure that you can't factor any further, okay? Make sure that you have factored completely before you say you're done. Because if you don't, then you would have stopped here and you would have said, hey, we can't do anything more. Okay, so that is important to always check for. Let's take the next one. Let's say that we have 1 minus a squared over a squared minus 2a plus 1. And again, try it on your own. 1 minus a squared. This is a difference of squares. 1 is a perfect square and a squared is a perfect square. So this would become 1 plus a times 1 minus a. Okay. So just because it's 1 minus a squared as opposed to a squared minus 1, it doesn't change the fact that we have a difference of squares. And then we need two numbers that add to 1. But that add to -2 but multiply to 1, and that would be -1 times 1. So we would have an a minus 1 and an a minus 1. We would have two of these here. Okay. And we already know that when they're opposites of each other like this, they cancel and they're equal to a -1. Okay. We know that from up here, so we've seen this before already. So these cancel, and we just get a -1 up here. It's -1 over 1. Okay, -1 over 1. If it were -1 over -1, then that would just be a +1, so that wouldn't make sense. So this is a +1 down here and a -1 on top. You can move the negative to the bottom if you want, okay? 1 over -1 is also -1. So that's up to you. You would get full credit either way. It's just that typically we like to put the, if we're saying that something is -1, we like to put it in the numerator because it's like -1 is a whole number, so why would we write it as a fraction so that it needs to be written as a fraction? Okay, so let's simplify. This is now -1 times 1 plus a over a minus 1, and that's it. We don't need to write the 1 here. We could just write negative. So -1 plus a over a minus 1. And that's it. We can't do anything. Even if we distribute the negative, we would have a -1 minus a. That's not the opposite of this, okay? So even by distributing a negative, you still don't get the opposites here where you can cancel it out and make it a -1. So this is your final answer. And because we've been writing domain, we'll continue to do that. So our variable is a, and you would look at this. Remember, you look before you cancel, but both of these are the same. So it really doesn't matter that one of them canceled. Both of them tell us that a can't be 1. Okay, next one. So our next one is x minus 4 over x squared minus 6x plus 8. And again, we just factor the numerator, factor the denominator. Remember, there is nothing that could get canceled until after you factor, okay? So x minus 4 can't be factored any further. We're just going to leave that. But x squared minus 6x plus 8 can be, because we do have two numbers that will multiply to 8 and add to -6. Those two numbers are x minus 4 and an x minus 2. So the x minus 4 over x minus 4 is a 1. So here's the thing to be careful of. If everything cancels in the numerator, it does not mean that there is no longer a numerator. It means the numerator is 1. So your answer here is 1 over x minus 2. The x minus 2 is in a denominator. We do not move it out of that denominator. It never moves. Okay, so I've seen some people where everything cancels in the numerator and all of a sudden they'll write x minus 2. If it's in a denominator, it can't be moved to a numerator unless you change the exponent to a -1, which we don't want to deal with at all. We don't want to put in exponents when there aren't, okay? So this is 1 over x minus 2. That's another reason why I like to put the 1 in the numerator here, okay? And when we do the domain, remember to look at the original, not after you canceled, but before you canceled. So our variable is x, and we're not going to look here, we're going to look here. So here there are two things that we can't have. We can't have a 4, and we can't have a 2. So here you're always going to look at the denominator before canceling. you're doing is reducing. You're not doing anything extra. So let's just start with multiplication, okay? So when we have two rational expressions that we're multiplying, I'm going to change the color of this. I don't want you to get confused with our annotations here versus the things that are important. Multiply two rational expressions, we can just extend our fraction bar. That's the bar that separates the numerator from the denominator. And then we're just reducing. So we factor the numerator and denominator. Then cancel common factors. So let's take a couple of examples. We don't have to do a lot of these because it's essentially the same thing as what we've just been doing. So let's say that we have 3x minus 12 over x squared minus 4. And we're going to multiply this by x squared plus 6x plus 8 divided by x minus 4. Okay. Well, essentially, now how you do this, I said extend your fraction bar and then factor and cancel. And that's absolutely true. That's how you would go about doing this. Some of you may prefer to factor first and then extend the bar. So that's what I'm going to do. The reason why I would do that is so that you don't have to worry about where you need parentheses. Okay? Because by factoring, you're automatically putting them in. So let's just go through and make some notes. Okay? So the 3x minus 12, this is linear. But one thing that you should always check for is, does every term have a common factor? And in 3x minus 12, you do. So make sure that you factor this out. So this one has a common factor of 3. This one is the difference of squares. So we're going to keep that in mind as we do this, okay? So 3x minus 12, it has a common factor of 3, so we're going to just factor out the 3. And we get an x minus 4, okay? Then in x squared minus 4, it's a difference of squares. It's an x plus 2 times an x minus 2. And since we're leaving these separate, I'm going to write this separately. You don't have to. Again, you can combine it right away. I'm doing it separately just so that you have it in front of you and you see exactly what we're doing. So in the bottom here, there is nothing to factor, so we can leave this as x minus 4. And then x squared plus 6x plus 8. Two numbers that add to 6 and multiply to 8 are x plus 4 and an x plus 2. So because we're going to just combine, put parentheses around everything, okay? Just to be sure that you're not messing up order of operations. And then this is what we mean by extending the line. This is one big fraction. Okay, now I'm going to rewrite this as one big fraction. You do not have to do that. You can skip this next step. I'm doing it so that you see that all we did is when we multiply, this is all that we do. If we go back to the very first thing that we talked about, here we said when we multiply fractions, we multiply across. So 3 times 4, 2 times 2, 7 times 5, 6 times 6. Okay, so that's what we're doing here. So this becomes 3 times x minus 4, x plus 4, x plus 2 over x plus 2 times x minus 2 times x minus 4. And if you want, you can either skip this or you could skip this. It's up to you, but obviously you need at least one of these to show what the factors are, okay? And then we're just gonna cross out common factors. So we have an x minus 4 both on top and on bottom. And we have an x plus 2 both on top and on bottom. So now we're just looking at what's left. Be careful that you don't miss something. So we have a 3 and an x plus 4 in the numerator. And then in the denominator, we have an x minus 2. This is it. Okay, there's nothing else to write here. And because we've been doing it, I'm going to put in the domain, but you don't need. You typically won't need to unless it says, what is the domain? So it's x, and remember you look at the originals, okay? So you're looking at it before you cancel anything else. So before we cancel anything out, we have an x plus 2, and an x minus 2, and an x minus 4. So our x can't be negative 2, it can't be positive 2, and it can't be a 4. Okay, that would be the domain. Let's take another example. Let's say that we have y minus 3 over y squared minus 6y plus 9, and we multiply by y minus 3 over 4. Okay, so we can just skip through here, okay, and write this all as one giant fraction as we go through and we factor. So we have a y minus 3. This is our first fraction. We need two numbers that multiply to 9 but add to negative 6. So that's actually two y minus 3's here. And then we have a y minus 3 again over 4. So all we did is extended this line, okay? It's just an extension of the line so that it's all one fraction. And then we're going to look to see what we can cancel. Well, we have a y minus 3 and then y minus 3, so that's one of the ones that we can cancel. And then we actually have a second one in both the numerator and the denominator. Okay. And remember, when there is nothing left in the numerator, there is a 1. Okay, y minus 3 over y minus 3 is 1. So what are we left with? This is a 1 over 4. Okay. And again, because we've been writing domain, I'll write the domain here. It's just y such that y can equal 3. And that's it. Okay, let's take a look at division. Okay, so Let's do it with numbers first, and then we'll do some simple expressions, and then we'll go to ones that are more like this, okay? Or at least one that's more like this. So let's go back to numbers. We didn't do this with numbers, we just did it with the P over Q, the P over K divided by Q over K. Let's say that we have 3 over 7 divided by 6 over 5. Okay. Now, if you remember, we said we don't like fractions within fractions here. This is called a complex fraction. We don't like this. So to get rid of it, we multiply the bottom by its reciprocal. Because the 5s will cancel and the 6 will cancel. And then we won't have a fraction down here. But we can't just multiply the bottom. We have to multiply the top too. So notice what happens when we're dividing two fractions. This is actually turning into a multiplication problem, okay? It's turning into the numerator times the reciprocal of the denominator, because we multiplied the bottom by the reciprocal, but that just canceled everything out in the bottom. So now it's just this new multiplication problem where it's the numerator, sorry about that, it's the numerator times the reciprocal of the denominator. And we know that from here, it's just a multiplication problem. We just multiply straight across. And we're still going to try and reduce. So 15 and 42 are both divisible by 3. So we get a 5 here, and then we get a 14 on bottom. Okay. So division, when we divide, what we're really doing is we're taking the numerator and multiplying by the reciprocal of the denominator. So if we look at another example, just written in a slightly different way, let's say that we have 2 over 3 divided by 8 over 5. Well, this is the same thing as 2 over 3 divided by 8 over 5. Okay, so here we do the same thing. We multiply both the top and the bottom by the reciprocal of the denominator, but when we do that, it really just turns into 2 over 3 times 5 minus 8. Times 5 over 8, sorry. 2 over 3 times 5 over 8. So notice what we did here. I'll put this in blue. We took the reciprocal of the second fraction and multiplied. So we took the second fraction, we turned it upside down, we took its reciprocal, And now we're multiplying. So we changed our division problem into a multiplication problem. And now we can multiply straight across like we did before. This becomes 10 over 24. Always reduce your fractions. These are both divisible by 2. So we get 5 over 12. Okay? So this is what we do with rational expressions. We do the same thing. We take the reciprocal of that second fraction and then we multiply. Okay? So we're taking the numerator and multiplying by the reciprocal of the denominator. So if we divide rational expressions, I would still factor first. The reason why I would factor first is because when you find the domain, you need to find the domain of the original problem. So you're going to be looking at the denominator of the second fraction before you flip it. Okay? So that's why I would factor first, because then it's going to be easier for you to find the domain. Then you're going to flip your second fraction. Now, to be mathematical about it, when we say flip, we mean take the reciprocal. And then you're going to multiply. And I'll write this down. When you find the domain, if you're being asked to, you're finding the domain of the original function. So before taking the reciprocal. So we don't have to do a lot of examples of this. We'll just do a couple. So let's say that we have a squared minus 5a plus 6 over a squared minus 2a minus 3. We're going to divide this by a minus 5 over a squared plus 3a plus 2. Okay, so the first thing that we're going to do is we're going to factor everything. So a squared minus 5a plus 6. We need two numbers that add to negative 5 but multiply to 6. So that's going to be a minus 5 and a minus 1. Then we need two numbers that add to negative 2 but multiply to negative 3. So that's going to be a minus 3 and a plus 1. And I'm going to write this with division. I'm going to do an extra step here. You can skip this step if you want, but you may not want to because this is going to tell you what the domain is. So here, the numerator can't be factored. But then we have two numbers that multiply to 2 but add to 3. So that's 2 and 1. Okay, so from here you would write the domain. I would do it at this step right here. So we have our a, and in this case a is not equal to 3. That comes from the first denominator. A is not equal to negative 1 comes from the second. From the second factor, and a not equal to negative 2 comes from here. And this, we already took care of this. Okay, so this came from the a minus 3. This one came from the a plus 1. And this one came from the a plus 2. Okay, so now from here we can flip the second fraction. So this gives us a minus 5 times a minus 1 over a minus 3, don't forget your parentheses, times a plus 1, and then we're multiplying by the reciprocal. So this becomes a plus 2 times a plus 1 over a minus 5. And now we can look for what cancels. So we can write this all as one fraction. I'll do that here, but you absolutely don't have to. Okay, this is an extra step that is completely unnecessary. Remember that this last a minus 5 gets parentheses, right? Completely unnecessary. You don't have to do it, but it's there. We didn't need a parentheses up here because it was in a separate fraction. But again, it's never a bad idea to stick them in there just for your own benefit. So now we're looking for factors that are in common. Remember, a minus 1 and a plus 1 has no relationships whatsoever. We have an a plus 1 on top, we have an a plus 1 on bottom, we have an a minus 5 on top, and an a minus 5 on bottom. So what are we left with? A minus 1 times a plus 2 over a minus 3. And that's it. Okay, let's do one more. Let's do 4. I'll do this in a different color so you know it's a different problem. 4x cubed over 7y squared times 6z to the 5th over 5x to the 6th. That's a 6. Divided by 24 z squared over 35x to the 6th. Now this one, we don't have to do any sort of factoring. All we have to do is multiply. So we can have these 3 fractions all multiplying together, but first we have to take the reciprocal of this last fraction. So what we're left here with is 4x cubed. We could put this all in the same fraction times 6z to the 5th, but now it's 35x to the 6th up here. And then we have a 7y squared, a 5x to the 6th, and now we have a 24z squared on the bottom. This is an exponential expression now, but we want to multiply the constants. I would encourage you to try reducing first, just because it'll be easier to reduce when the numbers are smaller. So in other words, 4 times 6 is 24. So 4 times 6 cancels out with this 24. And I'll put this in purple here. 7 times 5 is equal to 35. So the 7 and the 5 cancels with the 35. So we actually don't have to do any multiplication of constants in this particular case. So here's what we're left with. x cubed, z to the 5th, x to the 6th, over y squared, x to the 6th, z squared. And there are lots of different ways that you could do this. I'm going to do it the same way that we've done all of our other exponential expressions, where we combine across, then combine vertically, and then get rid of negative exponents. Okay, so we combine across, we get x to the 9th, z to the 5th, and then we get, this is just y squared, x to the 6th, z squared. Okay, so we combined, this is a 2. So we combined horizontally, and then I'll combine vertically, and then I'll write it in. 9 minus 6 is x cubed. 5 minus 2 is 3. And then you can keep this y squared on bottom. There's no reason to make it negative. Okay, so we combine horizontally. And then we combined vertically. So here we didn't have to do any factoring, but what we had was an exponential expression. Okay. This was subtract exponents. And this one was add exponents. I'm not going to do any more examples of division because essentially we've done examples because we've multiplied. So the only difference is that you're flipping the second fraction and you're multiplying. So it's one extra step, just flipping that second fraction. And the multiplication is just like the reducing. You just have to extend that line. So they're all essentially the same. So we don't have to do any extra examples here, but as you do this on your review sheet, there will be a lot of examples. Okay, and that's it. Our next lecture is going to look at addition and subtraction, and then we'll also use that to solve equations.